The problem says Hulky and Bulky, two UPS workers, decide to race each other up a flight of stairs when the change in Y equals 4 meters at the warehouse. Hulky, whose mass is 120 kilograms, makes the climb in 3 seconds, while Bulky, 150 kilograms, took 4 seconds to make the climb. Complete the LOL diagram for each and determine the amount of work each did to reach the top of the stairs. So for Hulky, the initial of all of these are 0 because it's not a spring and he's on the ground. I set the starting point at 0, like right here, and then he's not moving, so this doesn't have any energy either. And then what's involved are the stairs, the earth, and Hulky's doing the work. So at the end he's above the starting point, so that's why everything else has an X except for the UG because he's above 0. So the work equals UG and then the UG equals MGH. So I plugged in what I knew because Hulky is 120 kilograms, and then I multiplied that by 9.8 for the gravity and then times 4 for the height. Oh wait, no, for the seconds. And then I got the work equals 4704 joules. And then for Bulky, it's the same thing for the starting and final. So then I plugged his numbers in and I got 5880 joules. So overall, Bulky did more work. B. Determine the power of Hulky and Bulky, who is more powerful. And power equals work divided by the time. So the work of Hulky is 4704 joules and then divided by 3 seconds, so his power is 1568. And Bulky was 5880 joules divided by 4 seconds, and that equals 1470. So Hulky has 98 joules per second more power than Bulky does. And then number 6 says, suppose the spring below has a spring constant of 50 I don't know, I think that's newtons per meter, I don't know. The box has a mass of 8 kilograms and rests on a surface of negligible, whatever that says, friction. Okay, so A says in the diagram at left, the spring was compressed 4 meters. How much work was done to compress the spring? So the equation for the spring is 1/2 K times the change in X squared. So I just plugged in the numbers and got 400 joules for the spring constant. B says, suppose the box was released from the spring. Diagram at right. How fast would the box be moving immediately after the spring reaches its equilibrium length? So then I took because it's moving this time, so I took 1/2 the mass times the velocity squared, and I plugged that in, and I got 3.162 meters per second.